In this lecture, we learn about turbo codes and the iterative decoding methods of turbo codes. Actually, turbo codes have a concatenated structure. Concatenated structure means that there are two encoders connected in serial. So, for example, the first encoder has the code rate of N1K1 and the second encoder has the code rate of N2K2. So the overall code rate of the concatenated structure of turbo encoder is K1 K2 divided by N1 N2. So in fact, why we are using the concatenated structure? In fact, this helps us to uh, improve the error correcting capability of the code. For example, if the first encoder can correct two errors and then if it exceed uh, the two errors, then it will be corrected by the second encoder. So, but sometimes this concatenated structure is not enough to control the error burst. A long string of errors, if comes, so it cannot be handled by the encoder. So how can we distribute this error string? The only way we can distribute it by using interleaving. So we are using interleaving before encoding the message and de-interleave it before decoding the message. So interleaver in fact distribute the burst of errors and improve the error correcting capability of the code. For example, if I interleave the message in such a way that I transmit a fifth symbol after the first symbol, so it means uh, I transmit symbols after an interval of four symbols. So it means the error burst can be spanned for 4 bits or 4 symbols. Then uh, it can be spanned over only one word. So that interleaving can be added to control the error burst before the encoder 1, and similarly the interleaving can be performed before the encoder 2. So the interleaving structure is depend that what type of encoder we are using. For example, the interleaving for a convolution coder is different than we are using for RSC encoder. So the coder 1 and coder 2 can be similar, or can be of different form. So the interleaver for coder 1 can be different from the coder 2. So actually in this lecture we emphasize on the iterative turbo decoding process. So we are not going into the detail of the concatenated structure of the codes and the interleaving methods we are using in this uh, concatenated structure. Another important thing is that previously in convolution codes, we are using uh, a soft decoding method. Actually, that soft decoding method have uh, the soft input, but the decision is at the bit level. Either it is 1 or 0. So we have a hard decoding. So that is the soft input, but hard output. But in turbo decoding method, we have the soft input and soft output. So it means that the output will be fed back to the decoder and it will improve the level of confidence of the decoding method. So by this soft input and soft output decoding, we have a significant uh, performance gain that the bit error rate probability of 10 raised to power minus 5 can be achieved at 0.7 dB. So at such low EV by naught, with just a code rate of 1 by 2, we can achieve the probability of error 10 raised to power minus 5. That is, in fact, is the advantage of soft input and soft output decoding method. So we need to learn that what is this soft input, soft output decoding method. So to learn this decoding process, so we recall from the previous study that we have the decision of the binary communication channel based on posteriori probability. A posteriori probability can be determined by the PDF of the signal with the priori probability divided by the probability of the uh, overall uh, overall communication. So this overall communication is in fact is bounded by P of X. So this in fact uh, posteriori probability of binary channel will comprise of uh, the likelihood of two posteriori probability comparison. So this comparison is in fact uh, is depend on the comparison of the posteriori probability. So um, actually, in fact, we have the random signal, and that random signal is in fact is a function of this random variable x, and that random variable x is in fact uh, determines the PDF of the uh, Px given d is equal to 1 or 0. So actually you have already studied it, so uh, you can easily grab this idea that if this x is the voltage level of the say or the signal element, so we can define the probability with a function of uh, p of x uh, given d, and we are comparing the likelihood of these two PDFs, that is L1 and L2. For example, if somehow we receive a value uh, in case of -1, we receive this value. So uh, so it will be considered as 1. So this is in fact is the uh, two signal class case, and in this decoding process we will use this uh, binary uh, communication. So we have the maximum a posteriori probability criteria, that we compare the posteriori probability of the two signal, and that criteria is called maximum a posteriori probability criteria. So in fact we are using the log likelihood ratio in turbo decoding. So in fact, if you consider this expression, so you can have the log of this divided by log of this, and the log may split these two probabilities into the two stats. One is in fact is the one is in fact is the channel stats, and the other is in fact is the data stats or the priori probability of these two functions. So in fact, uh, we have term as the log likelihood of the posteriori probability will be in fact is the log of the channel stats into the log of the priori probability of the data. So in fact, this is termed as L of the channel, L of the channel, and it is in fact is termed as the L of the data. So this is in fact is depend on channel stats. So this channel stats will along with this priori probability will help us to determine the log of the posteriori probability. So in fact, the log of this value is in fact is a real number. In fact, that is the real number. And on the basis of that real number, we have the soft decision out of the detector. So let's see that how we can modify this. So the the expression can be modified as that the uh, estimated data bit of the detector is in fact is the channel uh, stats and the data value which is known. So we can estimate the value of this LD by expressing the extrinsic value of the data weight that comes from the iteration. So if I substitute the value of this estimated value in here from this value, so in fact we will have this expression for the data. So basically the modulator often produces soft decision which transfer to the decoder. A decoder could be called a soft input. hard output decoder because the final decoding process are bits. So this is in fact a soft input hard output decoder, as I told you earlier. And in our case, we are implementing soft input, soft output decoder. So this is in fact is the clarity of the expressions we have learned here. So this expression are not clear here, but we can clarify it in this diagram. Actually, what is this? This is, in fact, we start the input to the decoder. So first input to the decoder is, in fact, is the priori probability knowledge. So this, in fact, is the input to the decoder is the priori probability or the known probability, and that value is 0. Initially, we gave the value 0 to the encoder. So this value will be refined based on the extrinsic value output of the decoder, and on the basis of this extrinsic value we have the new value of this LD head. So that value comes here. Now let's see that this LD head use the two things. What one thing is this, the estimated value of the data bit. So this is, in fact, we know that the channel stats and the LD are, in fact, these two values. These two values are added to give us this a posteriori value of this log likelihood ratio. So this is, in fact, is L C of x LC of x plus LD L of D. So these two values, if you go back and see the functions, so what is this? This is, in fact, is LC of x, and this is, in fact, is L of D. And what is this? That is L dash D hat, which is in fact is the posteriori probability of this. So this term is in fact is the channel stats, and that is in fact is the prior knowledge of the data bits. So these are in fact separated in two parts, and that knowledge L hat D hat is derived from these two stats. And here we L hat D hat, the post story probability will be come out from this LC of X and LD from here. Now the extrinsic value, actually that decision, previously what we have this value and we will make a hard decision. But no, here we have this value and we will add the extrinsic value. We estimate the extrinsic value based on the extra bits of the encoder. Based on the extra bits of the encoder, which is n minus k. So this extrinsic value is calculated from these n minus k bits of the encoder, and that n minus k bit decision will be fed back to this will be fed back to modify the value of L of D. So this value uh, will be this value will be fed back to the next iteration. So the first iteration, so we have increased the number of iterations. So we increase the number of iterations. So the BER will be reduced. So that's works at very low power, because by increasing the number of iterations, we are increasing the confidence level in our decision. So it means that the soft output decoder will help us to decide more about the correct answer. So this will be more clear in the examples. First, I tell you the log likelihood functions. So there is, in fact, you are familiar with this. This is modulo 2 sum, and the modulo 2 sum of two data bits. If we take the log of this, so that would be in fact represented by this symbol. So that is in fact is proved mathematically by this equation, but we can simplify this as -1 signum of LD1 and signum of LD2 into mean of LD1, LD2. So first I clarify this. It's not, for example, LD1 value is a numeric value. For example, its value is 0.1. So the output of this is 1. And if it is minus 0.1, that means it is less than 0. So the output of this function will be minus 1. So any value which is less than 0, so it generates minus 1. Any value which is greater than 0, it generates plus 1. So plus zero point 0.1 is greater than 0, so it will generate plus 1. So similarly, the minimum of these two values can be determined. So this is in fact is the plus 1, minus 1 and nothing. So if the value of this is 0, so the answer will be 0. So it's not possible that it will be exactly 0 in the practical case. So if it is 0, so the all the term will be 0. So in fact, this is nothing but science. So it is in fact is a sign, and it is in fact is a sign, and it is also the minus 1 sign. And we have to pick the minimum of these two values with this sign. So that is what this term means. So another log likelihood algebra is that if you sum up a very high value, so in fact it returns the it returns minus L of t. If you add a very large uh, number in it, so it gives you the negative value, or if you add a very small value, so it returns a very small value. So next, move forward. So we take an example. So that example will clear the concept. Uh, and in this example, uh, we have K1 rows and K2 columns. K1 rows and K2 columns. So we have uh, the parity calculated horizontally, and we have the parity calculated vertically. So this parity is in fact is N2 minus K2 bits. So in fact you assume it as a two encoders. One is adding the horizontal parity with a code rate of K2 by N2, and that parity is in fact is N2 minus K2, and the vertical is in fact is parity will be added by another encoder, and that has a code rate of K1 by N1. And so on the basis of this, we calculate the components of the code to have a soft output decision. Initially, we sum up these two values, you know, and and we take the value of this is 0. But later on, we have to add the third component in it, which is the extrinsic value, uh, which modifies, actually this extrinsic value will modify the value of this L of t. So this L of t hat will be the sum of this second component and the third component. If you go back and see the example that this new value of soft output is based on this extrinsic value, which we have calculated on the basis of this n minus k bits and the parity. So how we calculate this extrinsic value, we have not yet discussed. So we move forward, and I will tell you that how to calculate this extrinsic horizontal and extrinsic vertical value to modify the value of L of D to L of D estimated, and have it fed back for the next iteration. So, in fact, this extrinsic value horizontally calculated from the same equation we have learned previously. So, what we have learned previously, we know that this equation, in this equation, if we have to find this extrinsic value, so what I move this to here, and I move this to here. Actually, I explain that why we are taking the log. Log help us to change it to some numeric values. So all these components are just a number. So it helps us to have the real numbers, and on the basis of these real numbers, we can have the confidence level of deciding the two data symbols 1 and 0, right? So if we move these two components on the other side, so we can find the value of this, right? So that is very simple. So we have this horizontal calculation. So the next time I'll take uh, I actually there is a rule that uh, we have this horizontal extrinsic ratio for the vertical decoding. For the vertical decoding in step 4. So this actually uh, here we take L of D as the, so this horizontal extrinsic likelihood ratio is used for the iteration of vertical decoding. So next, the vertical iteration is taken as L of D, and we use from it here and repeat the steps 2 to 5. And in this way, we keeps on iterations, and every time the estimated values of L of D is channel of X, and that is the extrinsic horizontal and extrinsic vertical ratios of the estimated data width. ठीक? Now go on with some real data. So we extend the example. We have this transmitted data sequence. The same data sequence I have given you in the assignment. So it will be transmitted in this way that we are transmitting D1, D2, D3, D4. So, and P12, P34, and P13, P24. So that can be written as D1, D2, D3, and D4. And this is P12, P34, and P13, and P24. If we know the message 1, 0, 0, 1, so we can write D1, D2, D3, and D4. And the parity is calculated by this. So P12 is calculated by the exclusive OR of this, which is 1. And P34 is calculated by the exclusive OR of this 3 and 4, and that is 1. And similarly, the vertical parity is calculated. Now for the channel stats, that is in fact is given that the channel stats are in fact if you calculated is uh, is by 2 sigma square x of k, and if the variance is 1, so you can take it as 2x of k, right? And 2x of k means whatever the channel stats, you multiply it by 2 and you will get these values. So what are these channel stats? In fact, if you are considering an AWGN channel and the data is given, so you can simply multiply it by 2 and you will take the value of this. If it is mentioned that the noise variance is 1, and in our assignment we have also considered its variance is equal to 1. So we didn't learn that how can we calculate the extrinsic ratio. So the estimated d value of this is calculated by these two components, and for the next iteration we have to add the extrinsic value, which is this. So this extrinsic value is horizontal and vertical. So how to take the extrinsic value? For example, we are calculating the data bit 1 and we are calculating the horizontal extrinsic likelihood ratio. So for horizontal likelihood ratio, we take the data bit to the channel V channel X2 plus LD2, and we have the function, this addition function for log addition function, and then we have the channel statistics for X12. So if we are calculating the horizontal, so just look it here. Okay, we have 1, 2, 3, and 4. We have this sort of uh, bit positioning, and in fact here we have the parity 1, 2, right? Parity 1, 2, and parity 3, 4, 3, 4, right? So here we have parity 1, 3, and here we have parity 2, 4. So for data bit 1, we have the channel stats for X2, data bit 2, and the channel states for X12, right? So if you see here, so you have the channel states X12 here, and you have the channel states of X2 here. This is the channel states for X2, and this is the channel states for X12, right? And what about LD2? For LD2, we have uh, we have the value of LD2. Uh, we have the value of LD2 initially. Uh, we have the value of this is LD2 is 0 here, right? Initially we have its value 0. So similarly, from the equations uh, we have we calculate the values of this in the table. So we have its value calculated from the equations, and we have this the horizontal and vertical extrinsic likelihood, and we have the original channel measurements. So what we will do, so we will sum up these two values here, right? So similarly, the corresponding values are summed up, and we will have the new values. Here you can see that our message is 1, 0, 0, 1. So here we can decode the message correctly, but the confidence level is low. So we will see the result after the fourth iteration. After fourth iteration, we have the results improved to 2.6, minus 2.5, minus 2.6, and 2.5. So here we have decoded the same message 1, 0, 0, and 1. But here the confidence level is very high. So actually you need to practice it, and you need to solve the problem I have given in the assignment, and you can take help from these equations. And I upload the supporting material related to this problem, and then you can solve it. Because without practice, you cannot learn how to make the next iteration. Because in the next iteration, for horizontal extrinsic likelihood ratio, you will use the vertical iteration. And for the second iteration of the horizontal uh, likelihood ratio. You will use it in the second vertical uh, likelihood ratio. So, this is all about today's lecture, and hopefully in the online session we will discuss the problems related to this lecture. Thank you very much.